Good evening, everyone. Welcome you all to the problem solving session of NPTEL course on IC engines and gas turbines. Today I have some questions on IC engine syllabus, and we will go through these questions, and then I think from the next week we will be moving on to the gas turbines, as in the NPTEL course also it is moved to the gas turbines now. I hope I am audible to everyone. Okay. Moving on to the first question. The heat given to cooling medium in IC engine is about 50 to 60% or 30 to 40%, 10 to 20% or 60 to 60 to 70%. Can someone answer what is the answer? Chaudhary Manish, do you know the answer?
I think sir 10 to 20%.
No, actually the answer is 30 to 40%. You can, so it is a rule of thumb that from IC engines, if you give 100% energy as fuel input to the engine, this will be split into 33% useful mechanical energy. That is what we get as on the shaft, and we call it as brake power or brake energy, brake power. And then we will have 33% lost in the cooling system, and another 33% will be lost in the exhaust flow. Participants, please mute yourself. You can unmute only when you have to answer the question, or when you have a question to ask. Okay, thank you. So it's like out of one, you given 1/3 goes to mechanical and 1/3 goes to cooling, and 1/3 goes to exhaust. This is a rough estimate, and this obviously varies with the speed and load. So can we will see how the heat loss varies with the speed. So maybe if the load is constant, and for a constant load with higher speed, how would be the heat loss? Can you say, like, will it keep on increasing with the speed, or keep on decreasing with the speed, or to be constant? So the general trend is it will keep decreasing the speed. There are multiple physics behind this. One is, so this is for constant load. So one is the heat time available for heat transfer is becomes low when the speed increases. Is low for high speeds. And second one is the turbulence intensity is high for high speeds. So when the turbulence intensity high, that means the heat transfer is also becomes higher. But in net, the trend is like what I said. When speed increases, heat loss decreases. And there could be multiple factors. If you want to go through in deep, you can refer some textbook that is suggested in the course. Next question. Radiator is provided to cool the jacket water, pressurize the cooling water, provide additional water flow, none of the above. Can someone answer?
A.
Sorry?
Option A.
Sorry, I couldn't hear you.
A.
Sorry, I think your voice is not clear. The radiator is provided to cool the jacket water.
Yes, sir.
So, so the engine will have cooling water flowing through the cylinder block, and then it goes to the radiator, and then it goes back to the engine for cooling. And the radiator is generally provided with a fan, and in some cases there could be a cooling water pump here. These are depending on the kind of cooling system we have, and sometimes it is thermosiphon, or it is sometimes it is only thermostat which is controlling this flow and so on. Thermostat is used in radiators to control the velocity of water, control distribution of water to various cylinders, control the water temperature, control the pressure of water. Can anyone answer this?
Option C, sir.
Sorry, your voice is again not proper. So can you text in the chat? C. Yeah, control the water temperature. So I hope you know how the thermostat works. There will be some bimetallic strip which will deflect based on the temperature, and the bimetallic strip would be something like this, of different material. So when this is say this is aluminum and this is brass, I think generally it will be copper and brass. So when this gets heated up at room temperature, it will be straight, and when this gets heated up, the copper might expand more than the brass due to temperature, due to high temperature, and then because of this it will keep bending like this, and then this deflection will be used to open or close the valve. So here when temperature goes high, it will open the valve, and then it will control the water flow. So thereby the flow of the water is controlled based on the temperature. As the compression ratio increases, there is a large increase in heat rejection, large decrease in heat reduction, marginal increase in heat rejection, or marginal reduction in heat rejection. Can someone answer this?
Sir, what was the last question?
The last question is, thermostat is used in radiators to, the answer is, control the water temperature.
Just a sec, sir. Okay, sir.
Yeah, thank you. I think Subham has answered D. Can you explain how you said D? Okay. So when you consider a PV diagram, when you have I'm just considering an ideal cycle, ideal as standard cycle. So when you have a cycle which is compressing from 1 to 2, and then you have constant volume heat addition, then you have constant volume heat rejection, and then uh, heat rejection at constant volume. So now when you have a high compression ratio, uh, in case of the ideal case, you will not find any change, like when the compression ratio increases, I will mention that with dotted line. Then it goes higher. So there will be only proportional increase or decrease in whatever heat. So assume this is 3 4 and this is 3 bar 4 bar. So Q in minus Q out is equal to work done, right? Work. And for efficiency, you have work divided by Q in. So that is Q in minus Q out by Q in. It is 1 minus Q out by Q in. And efficiency with compression ratio, it goes like 1 by minus 1 by R power gamma minus 1. So this means when R increases, efficiency also increases, right? So when efficiency increases, if you put here, when efficiency increases, Q out decreases, right? We will assume the Q in is constant. So when efficiency increases, then to balance this, Q out will also decrease. And that is how we get marginal decrease in heat rejection. You can also consider from an ideal cycle, sorry, not actual cycle. When you have assume we are only compressing and expanding, and there is no combustion happening. So it goes and compresses like this, and then comes back in a comes back at a slightly lower pressure, because there is some heat rejection within this during compression and expansion. So because of this, while expanding, it will raise a lesser pressure when compared to the compression pressure raise. Now if you increase this compression ratio, you will go to a higher pressure. That means your temperature is also high, pressure is high and temperature is also high, and that means the heat transfer will also be higher. And because of the high heat transfer, now you will come back with a much lower pressure than compression pressure. And because of this, during the exhaust stroke, your heat rejection will be lesser, because most of the heat is rejected during the compression itself, because the temperature has gone high. So this is one way of explaining. If you have any questions, you can ask now. Okay. Moving on. Spark timing other than MPT results in less heat rejection, more heat rejection, no effect on heat rejection, none of the above. Can someone answer this? So MPT, how we achieve MPT is by varying the spark. Say we have TDC and we have some timing here, so we call as MPT. That means the torque is higher at this state. So
So the answer is B, more heat rejection.
other than MPT, yeah. So how we get is this curve is drawn for constant fueling or constant fueling, throttle position, etc. So we change only the spark timing, and because of this we see some difference in torque output. That means the efficiency also is higher at this point. Why? Because if you have the spark later, that means you will not you will burn the fuel later, and because of this you will most of the fuel energy will not used for the expansion of the gases, and it cannot push the piston, most of the combustion heat energy, and but it will go out as exhaust losses, and that is how you get more heat rejection when you move out of spark MPT time. So only at MPT you will have the minimum heat rejection, and beyond this you will have more heat rejection. Next question. Direct system of cooling air is one which cooling water flows by gravity. Hot water is continuously cooled and circulated. Hot water is simply discharged. Water is allowed to evaporate in the cylinder jacket. Does someone know the answer of this? So the answer is hot water is simply discharged. I hope this is covered in your topics. Yeah, just Isabel is right. Next question. In evaporative cooling systems, heat absorbed per kg of coolant air is Cp delta T, Cv delta T, latent heat of coolant, Cp minus Cv delta T. Yeah, the answer is latent heat of coolant, because in evaporative cooling system we use the evaporative enthalpy for cooling the system to absorb heat. So then that means the latent heat, which is the energy supplied to for the phase transition of the coolant from water from the liquid state to vapor state. Next question. Pump used in the forced cooling system is normally piston pump, gear pump, vane pump, centrifugal pump. Can someone answer this question? The answer is centrifugal pump. Why? Because for centrifugal pump for the cooling system, the viscosity of coolant is low. It's just like water, and it's not like an lubrication oil, and also the flow rate requirement is high. whereas for oil lubrication system, the viscosity is high and also the flow rate is not as high as a cooling system. So here centrifugal pump is a good choice for such application, and here positive displacement pumps are used. And also the pressure delta P, or the pressure by which the pump has to pump the fluid, is also high for lubrication system but low for a cooling system. And because so since delta P is high, only in lubrication system we use a positive displacement pump, which is generally gear pump or vane pump, but generally piston pump is not used in engine, only gear or vane pump is used. Next question. Advantage of liquid cooling system is dependent only on water supply, power absorbed by the pump is considerable, even cooling very cheap. Can someone answer this? Advantage of liquid cooling system. So among the options given, the best choice is C, even cooling. Superm has given B, power absorbed by the pump is considerable. So if the power absorbed by the pump is considerable, then it is a demerit, right? So it is not an advantage. Mostly that is why for small engines like 100 cc or 200 cc engines, we don't use a liquid cooling system, we use only air cooling system. And beyond this, like when you see some high performance bikes from KTM, Honda and etc., beyond say 250 cc or high, from 250 cc onwards, they will use liquid cooled. So why they go for liquid cooled is to have high cooling capability. So that means you can force more coolant into the engine, and you can transfer more heat from the coolant through the radiator to the air by having more fan or increase in the fan flow rate in the radiator, and that's how you can achieve high cooling rates. And you can also achieve even cooling. How this is so when you have say a 4-cylinder or 6-cylinder engines, this is from the top view looking at the say from the cylinder head. When you have air cooled system, the air flows only through the outsides, so that means the end cylinders will get cooled much more than the inner cylinder. So inner cylinders will operate always at a higher temperature when compared to the outside cylinders. Outside cylinders will be relatively cool. So this will lead to uneven cooling, and then the power output, everything will be different from different cylinders. That is why liquid cooling is an advantage in this. And cheap liquid cooling is obviously you add more components to the engine, and then it is not cheap. Only air cooling is cheaper. And one another advantage of air cooling is high reliability. So now you add, when you design an engine for air cooling, so that means when you design an engine for air cooling, you will ensure that the fins are sufficient enough and maybe even with the belt of the or the fan that is connected to the belt of the engine is sufficient to cool the engine properly. So that means you will have minimal parts for the cooling. That is only fins. Fins is not a active component at all. It can very rarely it can fail only with a physical damage or something, and fan can also is relatively reliable. But in case of liquid cooling, there are many components involved in it. So first thing is the cooling passage that you drill in the cylinders and so on, and these passage cannot be always very big. It has to be smaller, and if the water is or the cooling water is very corrosive, then these can block the cooling passages, and then you will not have sufficient cooling in some parts of the cylinder or the engine in total. And the other case is like you will have lines flowing from the cooling lines flowing from engine to the radiator and so on. So these will, and these can puncture, and then this can leak, the coolant can leak, and radiator itself is a very delicate component. You can see the radiator, like even by touching the fins of the radiator it can damage. So radiator is very sensitive for getting damage, and it is not so reliable. And because of these all additional unreliable components, the liquid cooling system becomes not so reliable. So for very high reliability, air cooling is used. So this is in case of defense applications. They prefer air cooling over liquid cooling. So even when the engine is very high, like 600 HP or 1000 HP engine, which is used in tanks, used for a defense application, they prefer to have liquid air cooling over liquid cooling. Limitations of air cooling system are applicable only to large engine. Cooling is fast, high working temperature compared to water cooling, all of the above. Can someone answer this? What are the limitation of air cooling system? Chaudhary Manish has answer C. Higher working temperature compared to water cooling. Yes. So because when you have water cooling, the temperature of the coolant can go up to say 120 degrees Celsius. But so that means when the coolant is there, it will ensure that the engine body temperature is less than 120 degrees Celsius. But in case of air cooling, it can go much higher than this temperature. So when you have air cooling, you will have a higher working temperature. The main purpose of thermostat in an engine cooling system is to allow engine to warm up quickly, prevent the coolant from boiling, pressurize the system, indicate to the driver the coolant temperature. What is the answer for this? The answer is to allow engine to warm up quickly. So when you have engine radiator system, this thermostat will open only, will allow the flow through the radiator or to the radiator only when the temperature goes beyond certain limit. So because of this, it will prevent the cooling effect before the set temperature is reached. So until the set temperature is, there is no much of cooling acting on the engine, so then it can warm up quickly. So when engine warms up quickly, you will have more advantages on better thermal efficiency and so on. So because of this, good running the engine at the optimal temperature is always desirable. And thermostat is one device which will help in achieve the warm up quickly. The radiator cooling tubes are generally made of rubber, plastic, brass, copper. Can someone guess the answer? The answer is copper, because copper has more thermal conductivity. So copper has high thermal conductivity and compared to the other materials. And nowadays it is only aluminum is used for to make it cost effective and also lightweight. Next question: water circulation in a thermosiphon cooling system is due to conduction currents, a gear driven water pump, change in the density of water, a belt driven water impeller. Can you answer this? I think Chaudhary Manish has answered C. Change in the density of water. Yes. So the answer is change in density of water. This I think we know in case of the radiator is kept below or above? I think the radiator will be kept above, right? So the only the cooled coolant will come down side of the radiator and enters the engine, and with the engine while cooling the engine, the coolant will get heated up, and because of this density goes down and then it will rise up and comes to the radiator to the top. So because of this the flow happens, and that is how the thermosiphon cooling system works. So the flow occurs because of change in density of water. The main purpose of fan in a liquid cooling system is to disperse engine fumes, pump cold air over the hot water, cool the external surface of the engine, drive airflow when the vehicle speed is low? Can you answer this? The main purpose of fan in liquid cooling system is to pump cold air over hot water. So we have this radiator. So the high temperature coolant enters the radiator and goes out. And air is blown across, the fans are kept here, and air flows through the over the tubes where the hot water comes. So it is to pump cold air over the hot water. Next question, engine overheating may be due to stuck radiator pressure cap, open thermostat, broken fan belt, excess coolant. Can someone answer this? The answer is broken fan belt. So stuck radiator pressure cap means the radiator pressure cap cannot be opened up because it is getting stuck, and that will not create any issue with the cooling system of the engine. And when the thermostat is open, it will always allow the coolant to flow out. So the warming up will be delayed, but engine will not get overheated just because of the open thermostat. When the fan belt is broken, that means the fan will not be spinning, so it cannot ensure airflow across the engine, and the airflow will get reduced from the design flow rate. So because of this, the engine will get overheated, and excess coolant is not a problem. It will because of excess coolant, the engine cannot overheat. So do you have any questions so far in any of the questions we saw earlier? Okay, if there are no questions, I will move on to the next problem. Now I have few problems where we shall find the air fuel ratio of the different fuels. So first we have gasoline equivalent octane, gasoline equivalent, which is octane, and this has a molecular formula of C8H18. So now to write the chemical equation, we have fuel plus air going in. So air can be represented by O2 plus 3.73 N2, and when here you can fill in some value, and then still the nitrogen and oxygen balance will remain the same. So this is assuming that for every 1 mole of oxygen in the air, there are 3.73 moles of nitrogen presented. Now we will have CO2. For stoichiometric, we will have pure combustion, complete combustion, that is CO2, H2O, and N2 alone in the products. So now we can assume some value m here, and then a, b and c here. Now we can calculate what will be the value of m. So now using carbon balance, we have 8 on the left hand side, and on the right hand side we have a times carbon plus, so we have only a, right? So only carbon dioxide on the right hand side has carbon. So we know a is 8, so that means CO2 is found out. Now we can have hydrogen balance. So hydrogen balance on the left hand side, it is only 18 moles on the left hand side. On the right hand side we have 2b, right? And the H2O we have 2b moles of hydrogen. So that means b, the value of b is 9. Now we can have oxygen balance. On the left hand side we have 2m, and on the right hand side we have 2a plus b. So we know, we have already calculated the values of a and b. 2a is 2 into 8 plus b is 9, which is 16 plus 9, which is 25. So this way, so this is 2m, right? So m is 12.25 by 2, which is 12.5. So now we know the balanced equation is C8H18 plus 12.5 O2 plus 3.73 N2 will give out 8 moles of carbon dioxide plus 9 moles of hydrogen water plus C. We can have nitrogen balance and find the value of C, but generally for the airfill calculation, airfill ratio, it is not needed, but still I will, for the sake of completion, I will do it. So nitrogen balance, on the left hand side we have 3.73 m, 3.73 into 2m, right? Because there are 3.73 nitrogen molecules, which has 2 nitrogen in each molecule. So we will have 3.73 into 2m on the left hand side, and we have C, just C on the right hand side. So we know the value of m is 12.5, so C can be found out 3.73 into 2 into 12.5. So that is 93.25. Actually on the right hand side we have 2C, because for every C there are 2 nitrogen atoms. So we will have 2 and 2 here, so that means C will be 46.625. So now we have found the balanced chemical equation. From this we will be able to calculate the airfill ratio. So we have 1 mole of C8H18 plus 12.5 mole of air, and air is O2 plus 3.73 N2. So these are in molar basis. When we have air-fuel ratio, we have mass of air by mass of fuel. So we need to convert this molar basis to mass basis. So for fuel we have 1 mole 1 into molecular weight of fuel times the this much grams of fuel we have. How molecular weight means gram per mole, and we had 1 mole of the fuel, then mole and mole will get cancelled, and finally we will end up with having grams on the numerator. So molecular weight is 8 into the molecular weight of carbon is 12 plus 18 into 1, because hydrogen molecular weight is 1. So with this we will have, you can also solve this in parallel and let me know the answer. What is the fuel mass? The answer is 114 grams. So we need 114 grams of fuel, and then we can calculate what grams of air we need. So to calculate air mass, we have 12.5 into molecular weight of oxygen plus 3.73 molecular weight of nitrogen. So this is 12.5, molecular weight of oxygen is 32 plus 3.73 into molecular weight of nitrogen is 28. Can someone answer this? So this turns out to be 1705.5 grams. So we have air fuel ratio is air mass by fuel mass. So air mass is 1705.5 divided by 114. So this is 14.9. So approximately 50. So this is how we in the previous problems we have found that the air fuel ratio of gasoline, we were directly using that the air fuel ratio of gasoline is 15, and this is how we have obtained the value. And this is only the equivalent molecular weight of gasoline that we have taken. So gasoline is generally assumed to be isooctane. But in reality, gasoline is a group of many hydrocarbons. And most of them are aromatic hydrocarbons like benzene and derivatives of benzene. By derivatives it could be methyl benzene, ethyl benzene, propyl benzene, and so on. Do you have any questions with the air fuel ratio calculation? So similarly, we can calculate the diesel equivalent air fuel ratio for diesel. So for diesel, we have C12H22. Sorry, H23. can write the chemical equation. I would have M times the air and A times carbon dioxide, B times H2O and C times nitrogen. So if I put carbon balance, it is 12 on the left hand side, and on the right hand side I have A, so that means A, the value of A is 12. And now if I have hydrogen balance, I have 23 on the left hand side, and on the right hand side I have B, so directly I've got the value of A and B. Now if I have oxygen balance, I have 2m on the left hand side, and on the right hand side I have 2a plus b, so that is 2a will become 24 plus b is 23, then we have 47, and m will be 23.5. Now for air fuel ratio, I have mass of air by mass of fuel, which is moles of air into molecular weight of air divided by mole of fuel into molecular weight of fuel. So moles of air is m into 1 plus 3.73, right? So rather we can directly write this as 23.5 into 32 molecular weight of oxygen plus 3.73 into molecular weight of nitrogen divided by moles of fuel is 1 into molecular weight of fuel is 12 into 12 plus 23. Can someone compute this? Can you follow what I am telling? Okay, the answer is 19.2. So that means for diesel the air fuel ratio is approximately 19.2. Similarly, we can see for methane, yeah, 19.19 is correct. So actually I had 19.1996, and this I approximated to 19. Now we can see for the methane. I think for methane it is relatively easy. So we have methane CH4 plus m times air, that is O2 plus 3.73 N2, and on the products we have A times of carbon dioxide and B times of H2O plus C times of nitrogen. Now if we put carbon balance, we get 1 is equal to A, and with hydrogen balance we get 4 is equal to 2B. So that means B is equal to 2, and with oxygen balance I get 2M is equal to 2A plus B. I know the values of A and B. A is 1 and then B is 2. So I have 2 into 1 plus 2, and then this is 4. Then I have M is 2. So I will have air fuel ratio as mass of air by mass of fuel. So for mass of air I have 2 into 32 plus 3.73 into molecular weight of nitrogen, which is 28, divided by mass of fuel. For fuel I have 12 plus 4. I have only 1 mole of methane, and 1 methane will have 1 carbon atom and 4 hydrogen atoms. So for 1 carbon atom it is 12 gram per mole, and for 4 hydrogen atom I have 4 gram per mole. So what is this value? Yes, 17.055. This is the air fill ratio for methane. So I think we can solve methanol and ethanol next. Methanol molecular weight is molecular formula is CH3OH. So this plus air, m times of air, that is O2 plus 3.73 N2 will give A times of carbon dioxide plus B times of water plus C times of nitrogen. If I do carbon balance, I have 1 on the left hand side and A on the right hand side. So value of A is 1. Then if I do hydrogen balance, I will have 4 on the left hand side and 2B on the right hand side. That means B, value of B is 2. And if I do oxygen balance, now the oxygen balance is little different from what we have seen earlier. Earlier the oxygen were present only in the air and not in the fuel. Now we have oxygen present in the fuel itself. So when we have such kind of fuels, the air fuel ratio is little lower, but it also happens that the calorific value of such fuels, calorific value of such oxygenated fuels is lower when compared to non-oxygenated fuels. And because of this we have to supply more kgs of fuel into the system, into the engine, to get the same energy output or power output. But the advantage is that you will have better combustion, because there is no there are very less chances of becoming the combustion becoming oxygen deficient, because oxygen is directly present in the fuel, and there is the time taken for mixing can be reduced, because you need only less amount of oxygen to be mixed for before combustion, for the proper combustion to take place. And because of this, you will have in diesel engines, you will have less soot emissions, less soot emissions, because of this oxygenated fuels. So now balancing oxygen, on the left hand side we have 1 plus 2m equal to, on the right hand side we have 2a plus b, and we know the value of a and b, which is 2 into 1 plus b is 2, so we have 4, and m will be 3 by 2, which is 1.5. So for air fuel ratio, we have mass of air by mass of fuel. So for mass of air, we have 1.5 times molecular weight of the single nitrogen component that we have, air component that we have taken, that is 32 plus 3.73 times nitrogen, that is 28. And then in the denominator we have molecular 1 into molecular weight of fuel. For molecular weight of fuel, we have 12 into 1 carbon atom, plus for hydrogen we have 4, plus for oxygen we have 16. So can you tell what is the air fuel ratio? Yes, the answer is 6.39. So as we see, when we for air fuel ratio for methanol is 6.39, whereas for AFR for methane was how much, around, yeah, 17.05. So this is the difference we get in having an oxygenated fuel. So that means mixing we need not focus much on the mixing of air fuel in the system. We can have very fast combustion, better combustion without formation of soot or unburned hydrocarbon, etc. Now we will have ethanol, which is C2H5OH. And I have carbon balance. On the left hand side I have 2, and on the right hand side I have A, so the value of A is known. Then with the hydrogen balance, I have 6 on the left hand side, and on the right hand side I have 2B, that means B is equal to 3. Then with oxygen balance, I have 1 plus 2m, similar to the previous case on the left hand side, and then I have 2a plus b on the right hand side, and 2a plus b will become 4 plus 3, which is 7. So value of m will be 3. Please correct me if I wrong somewhere. Now for air fuel ratio, I have 3 times 32 plus 3.73 into 28 divided by molecular weight of fuel. So for fuel we have 2 carbon atoms, so that corresponds to 2 into 12 for the molecular weight, and then I have 6 hydrogen atoms, so that is 6 into 1 plus 1 oxygen atom, that is 1 into 16. So can you compute this? Yes, the answer is 8.898. So this can be approximated to 8.9. So when there is when we have a methyl alcohol, we had 6.39. When the carbon atom increases, we had a large difference in AFR. From 6.39 it went to 8.9. But even for single carbon molecule, there are much difference when we have a single oxygen in the fuel itself. So when there is no oxygen, in case of methane we had 17.05, and when in case of methanol, when there is one oxygen, the air-fuel ratio is drastically reduced to 6.39. So you have any questions with these problems in finding the air-fuel ratio? Okay, if there are no questions, I will move on to the next problem. At injection pressure of 150 bar, spray penetration of 25 centimeter in 20 millisecond is obtained. If an injection pressure of 250 bar had been used, what would have been the time taken to penetrate the same distance? Assume the same orifice and combustion chamber density. The combustion chamber pressure is 25 bar. So how can I solve this problem? So this can be solved by using the simple orifice equation, where we have V is equal to under root 2 delta P by rho. So that means I can say velocity is proportional to root of delta pressure, and we have in terms of penetration length and time. So I would write S by T, or distance traveled by time taken, is proportional to under root delta P, and here it is told that only the pressure changes, and we need to calculate the penetration length for the same time. So I can further write this as S is proportional to delta P alone, because there is no change in time. Initially it is 20 milliseconds, and for 250 bar there is no different time that has been told. Oh, okay, we have to find the time taken. Okay, that means S is constant and we need to find the time taken. So then it's better I write it as T is proportional to S by root delta P. So now I have or I think it's better I write S by T delta is equal to constant. So S1 by T1 delta P1 under the root is equal to S2 by T2 under root 2 delta P under root delta P2. Now the penetration length is same, that means these two get cancelled out and we will be left out with T1 delta P1 is equal to T2 delta P2 under the root. So T2 is T1 into delta P1 under root divided by delta P2 P2 under root. So in the initial case the time 1 was 20 milliseconds. I have it at the same unit, and for the delta P1 I had 150 bar as injection pressure and minus the chamber pressure, which is 25 bar. Here we are dealing with only the delta P. That means if we have an injector with high pressure at the inside the injector at 150 bar and outside it is 25 bar, only the effective delta P will contribute to the velocity, to the flow. So that way we have under root 150 minus 25, and similarly for the second case we will have 250 minus 25 as delta P, and this should be in the root the formula. Can someone compute this? Yes, 14.91. What will be the unit? It will take the unit of the value 20 that we have given, so that is milliseconds. So T2 is 14.91 milliseconds. Do you have any questions in the problem? If there are no questions, I will move on to the next problem.
One question here, sir.
Yes.
Can you hear me?
Yes, I can
So
hear you.
if we are if we are asked to find out the orifice diameter, so how it will be is like how to compute? Is it like we have to have only very like around a 0.88 or something as orifice diameter, or it can be bigger to 1 mm, or how is it? I think this is specialized orifices, and I think it is manufactured through laser beam, right?
Yes. So these are manufactured sometimes old injectors were manufactured with mechanically drill bits. We get drill bits for up to say 0.3 mm diameter also.
Oh,
Okay,
okay.
so these are mechanical drill bits available, uh, and with hydro erection we can achieve diameters up to 0.15 or even
Is it?
125
Okay.
mm. Yeah. So these are the recent common rail injectors will is formed by hydro erection. Maybe laser is also used in some cases. These are the things that I know of. And so in such problems, if you are asked to find the flow rate, the area of the orifice, then you should have a indication of the flow rate. So here we deal with only the velocity and the delta P. So for this V equal to 2 under root 2 delta P by rho is sufficient. But if you want this one area, then we will have m dot as rho av, right? Now we know
Sorry, disturb. Is there any limitational number of 45s provided there? Is it like 8, 12, or what I heard standard is around 8 and 12. We can't go more than that. Is there any limitation as such?
yeah, like generally in CAD we see from 6 to 8, which is very common, and maybe some cases can go to 12 or something. I'm not sure, but but for mechanical systems earlier we used to have only 3 holes.
Okay. Okay. Okay.
Yeah.
Understand.
And
Yeah, got it.
why we want to go for more holes? I think uh, when the flow rate is high, yeah, it is generally achieved with a larger orifice or mm,
Uh-huh.
higher injection pressure. But I think if you want
Uh-huh.
to inject drill many holes around the small periphery, it is not so easy.
Okay. Okay.
The
Got
injector
it. Yeah.
tip, maybe you have seen the tip, it will be something like this.
Yeah.
Yeah, and the holes will be located in this level.
I understand. Yeah.
Yeah, and this
Sir, if you remember,
hmm.
yeah, sorry. Yeah, you go ahead, sir. I'll speak later.
Yeah, yeah.
Sir.
If you look from top, the entire diameter of this portion where the holes are present will be of
Uh-huh.
say 3 to not like 3 mm or 4 mm. Diameter will be like 3 mm or 4 mm.
I understand, sir. Yeah.
Within this,
Okay.
to put in so many holes is not easy. Yeah.
Understand. Sir, remember I had mailed you to meet you. This
Yes,
is
yes.
Ram.
Yeah, yeah.
Yeah. Can we meet this Saturday, sir?
Yeah, yeah. No problem.
Something I'm working on this. Yeah.
Yeah,
At
no
11
problem.
m, I'll be coming by. Okay.
Yeah, no
Fine.
problem. You
Thank
can
you, sir.
mail me regarding this. We can meet.
I've mailed you. I've mailed you. So
Yeah, yeah.
I'll come and meet you on this coming Saturday around 11 a.m. at
Yeah,
IIT Madras.
yeah,
Is that
yeah.
okay?
Yeah, yeah. No problem. We can meet. Yeah, again,
Thank
you
you, sir.
just put a reminder in the mail. I cannot note the timing now. We
Yeah.
can.
Yeah.
Yeah.
Now I'll send a mail. Just check with you now. Yeah.
Ah, okay, okay. Fine. Thank you.
Yeah. Thanks, sir. Yeah. Yeah.
Okay, if there are no other questions, we can move on to the next problem. So, this problem deals with the mechanical fuel injection system. Before the commencement of effective stroke, fuel in the pump barrel of a diesel fuel injection system is 6 cc. The diameter and length of the fuel line from pump to injector is 2.5 mm and 600 mm respectively. The fuel in the injection valve is 2 cc. To deliver 0.1 cc of fuel at a pressure of 150 bar, how much is the displacement of the plunger undergoes? Assume the pump inlet pressure of 1 bar. What is the effective stroke of the plunger if its diameter is 7 mm? Okay, so and the compressibility of the diesel oil is given, that is 75 into 10 power minus 6 per bar at atmospheric pressure. So we have given pump and then there is a plunger which commencing to pump the fuel, like the effective stroke is starting now, and while it is starting, the fuel in the system in the pump barrel is 6 cc and it has a line of diameter 2.5 mm and length of 600 mm. Then we have an injector, and this they call as injection valve, and fuel in this line is 2 cc. Now it has to compress from 1 bar because the initial inlet pressure is given as 1 bar, and it has to compress till 150 bar. During this compression we need to find and after compressing it has to deliver 0.1 cc of fuel. We need to find the displacement of the plunger. Now we know the initial volume and final volume. So generally the compressibility is given by delta V by V divided by delta P, and here delta V is V1 minus V2. So V1 is volume in the barrel, volume of fuel in barrel, plus volume of fuel in the line plus volume of fuel in the valve. So the volume of fuel in barrel and valve are directly given in terms of cc's, and we don't know, we have to calculate the volume of fuel in the line. So this I would say VB, and this is VL, and this is VV. So VL is pi by 4 d square into L, that is pi by 4 into it's better to have everything in terms of cc. So writing 2.5 mm in centimeters, it's 0.25 centimeters into 600 mm will become 60 centimeters, and I have square here. Can someone compute this and let me know the answer? So this is 2.945 cc. So V1 we know it is sum of the all three, that is for the barrel it is 6 cc, plus for the line it is 2.945 cc, plus for the valve it is 2 cc. Then on the total we have 10.945. cc of fuel has to be compressed, and to compress it to 150 bar we can calculate how much should be the displacement of the plunger by calculating delta V. So K is given as 75 into 10 power minus 6. This is equal to delta V by V by delta P, that is the V1 minus V2 divided by V1 by delta P is P2 minus P1. So 75 into 10 power minus 6 is V1 minus V2. So V1 we have 10.945, or I think delta V is alone enough. So we have delta V by 10.945 divided by 150 minus 1. So this is delta V is 75 into 10 power minus 6 into 149 bar divided by or into 10.945. Can someone compute this and let me know? The answer is 0.1223 cc. So that means if the plunger displacement has to be 0.1223 cc for the fuel to compress for this volume of fuel with the initial volume of 10.9 cc to compress from 1 bar to 150 bar. Now after compressing this, it has to further displace for delivering this 0.1 cc of the fuel. So that means total displacement of the plunger will be the initial compression displacement to increase the pressure from 1 bar to 150 bar, and then to deliver the fuel at 150 bar, that is 0.1 cc. So in total we will have 0.223 cc of the plunger displacement to achieve this delivery of 0.1 cc at 150 bar. So now we have got the plunger displacement in terms of cc, and if the diameter is 7 mm, we can calculate what should be the effective stroke. So displacement is pi by 4 d square into stroke length, and we know this is 0.223. Having everything in terms of centimeters, I can get it cc directly. So 7 I can put diameter in centimeters. It is mentioned 7 mm, so it is 0.7 centimeters into L. So L will be 4 into 0.223 divided by pi into 0.7 square. So this is 0.579 centimeter or 5.8 mm. So this should be the effective stroke. Do you have any questions in the problem? So I have only this many problems for today. If you have any questions on IC engine topic, on any other week content also, you can ask now, because from tomorrow, from the next week, we will have gas turbines.
No, sir, we don't have any questions.
Okay, if there are no questions, I think we can close the session now.
Okay, sir. Thank you, sir.
Yeah, thank you for participating.
And happy all, sir.
Happy Holi. Thank you. I will end the session.
Thank you so much, sir.